Okay, hello and welcome to our CGD seminar. So today it's my pleasure to introduce Dr. Shoichiro Kido, who's currently a postdoctoral researcher in the Applications Laboratory at the Japan Agency for Marine Earth Science and Technology, also JAMSTEC. Yes, okay. So he holds a PhD, which was awarded in 2020 in Earth and Planetary Sciences from the University of Tokyo. Shoichiro is currently working with Dr. Masami Nanaka on research related to the variability of the tropical and extratropical ocean and atmosphere, and on ocean modeling and data assimilation. He'll be talking with us today on nowcasting and forecasting of ocean jets and eddies using a semi-global eddy-resolving ocean prediction system. And as a quick reminder, if you're joining us virtually, we'll take questions at the end of the seminar, and you can put your questions into Slido. You just go to slido.com, search for the CGD seminar page, and we will address those questions at the end along with any in-person questions. So on to you, Shoichiro. And your mic's all good? Perfect.
Okay. Thank you very much for your kind introduction. And this is Shoichiro Kido from JAMSTEC, and it is my great pleasure to be here to give a seminar. So today I'd like to introduce our recent effort to nowcasting and forecasting of ocean jet and eddy using our newly developed quasi-global ocean ocean prediction system, which covers the global ocean with a horizontal resolution of 0.1 degree. So this is the outline of today's presentation, and I first start with a general introduction of the mid-latitude ASC interaction, and then provide an overview of our newly developed ocean nowcasting system, and then introduce our recent result on multi-year forecast of jet and eddy of the Kuroshio and Gulf Stream using that system, and conclude with summary and discussions. Okay, let's start from the general introduction of mid-latitude ASC interaction. This figure shows the composite of sea surface temperature and surface wind anomaly associated with the Pacific decadal oscillation. And left panel shows the positive phase of its PDO, and the right panel is a composite of negative phase of PDO. So during a positive phase of the PDO, illusion law is intensified, and the strengthening of a westerly wind here leads to enhanced evaporation and SST cooling. And the opposite situation occurs for its negative phase. So in summary, in case of atmospheric forcing of the ocean, SST and surface wind speed is negatively correlated. So this kind of passive forcing of the ocean by atmospheric forcing has been a traditional view of our extratropical ocean. However, such kind of passive nature of extratropical ocean have been changed thanks to the high-resolution satellite observation in early 2000. And the left panel shows a snapshot of sea surface temperature and surface wind near Japan and from satellite observation. And you can see a patch of high SST along the axis of the Kuroshio. And these regions correspond to those with narrow band of high wind speed. So this kind of situation is in opposite to the situation that I shown in the previous slide, and indicates the oceanic forcing of the atmosphere. So such kind of situation is not limited to this specific region, but it also applies to other part of the global ocean. And here we show a map of correlation between the high pulsed SST and surface wind. So it only extracts a mesoscale feature. And there are many regions with positive correlation, which is opposite to a conventional view of atmospheric forcing of the atmosphere. So these results suggest at frontal scale, there may be some kind of ocean to atmosphere feedback do exist. And subsequent studies have demonstrated that the impacts of sea surface temperature front is not limited to surface planetary boundary layer, but also extend to the entire troposphere. And this figure is taken from a famous paper, Nature paper by Minobe et al. And their study showed that on the warm side of Gulf Stream, the surface wind convergence, and such kind of atmosphere wind convergence leads to upward motion, and then creates a band of, narrow band of precipitation. And they further demonstrated that if this kind of frontal scale SST is removed in their ADCM, such kind of narrowly confined precipitation feature and atmospheric circulation pattern disappears, so indicating the importance of SST front in determining atmospheric circulation. And in addition to the SST front, recent studies have demonstrated that SST anomalies associated with ocean mesoscale eddies are also important for determining the position of storm track and a precipitation pattern. And this figure is from Ma et al. 2015, and they have conducted a series of atmospheric model simulation. And this figure shows the atmospheric precipitation and upper level zonal wind difference between experiment without eddy-related SST and original experiment. And they show that the removal of SST, mesoscale SST fluctuation leads to a southward shift of storm track and increase in precipitation in California. So as my debut in this debut here, complex nature of multi-scale air-sea interaction in the extratropical region having attracted broad attention in recent decades. So such kind of increasing interest in extratropical air-sea interaction motivated a Japanese researcher to organize intensive research project focusing on extratropical air-sea interaction. And a research project called the Hotspot 2 project is started from 2019, and it's still ongoing. And this is the website of this research project. And this is actually the subsequent project of Hotspot 1 project, which has ended in 2014. And in this project, we try to understand how extratropical air-sea interaction affect climate, predictability of climate and response to climate change. And there are several research tasks here. And in this presentation, under this project, I'm working on investigation of predictability of ocean currents and eddies using high-resolution data accumulated ocean general circulation model. So actually, this project, main focus of this project is Western North Pacific because it's close to Japan, but these interests are not limited to this specific region, but also extend to other Western boundary current region. So this is a general overview and the reason why we decided to work on this project. And let's move on to the next part, an overview of our newly developed ocean nowcasting system called JCOB FGO. As I mentioned in the previous subsection, an accurate monitoring of ocean current and jet of vital importance for understanding and predicting extratropical climate, and also play a role in, also has a very broad implication for other related fields such as fisheries or ship navigation. And however, most of existing global scale ocean reanalysis products are not sufficient, the spatial resolution of these products are not sufficient to explicitly resolve important feature of ocean fronts and eddies. And this table summarizes a horizontal resolution of commonly used ocean reanalysis product. And the right animation shows the snapshots of surface velocity field derived from satellite observation, and those from the Aura S4, which is a typical non-eddy-resolving ocean reanalysis product. And left one is Kuroshio region, and right one is Gulf Stream region. For the observation, you can see a narrow band of intense current jet, both for the Kuroshio and the Gulf Stream, and as well as energetic pinched off eddies associated with the jet. However, such kind of frontal scale feature is largely smoothed out in non-eddy-resolving system. And actually only 2 products covers global ocean with eddy-resolving resolution. But these products are not sufficient. The time period of these 2 products are not sufficient to cover the multi-decadal time scale. So this motivated us to develop a new global scale eddy-resolving ocean product to explore a predictability of ocean currents and eddies at multi-year time scales. Okay, so our strategy here is to expand the model domain of our regional system configured for the Western North Pacific to the global ocean. And in our group, we have developed a series of ocean nowcasting and forecasting system focusing on the area near Japan. And this family of products are called Jacob system. And we have several different hierarchy of system covering this area from rather coarse burn and to more nested one. But here, what we did is to expand this system model domain of this system to the global ocean to obtain 3-dimensional ocean circulation pattern and flow field in the semi-global ocean. And this slide summarized in overview of this our system. And this system that we name Jacob FGO, Forecasting Global Ocean, is a classic semi-global eddy-resolving ocean product, which is a global extension of the regional system. And this system provides an estimates of 3-dimensional temperature, salinity, velocity, and sea level field from the time period of January 1993 to present with daily resolution. This is achieved by combining information derived from satellite observation and in-situ observation with first, I guess, estimates of derived from the eddy-resolving OGCM. So this is we have assimilated several different kinds of data, satellite altimeter data, satellite sea surface temperature data, and in-situ temperature and salinity data from SIP observation and Argo profiles. And these are mediated by data assimilation scheme of 3-dimensional variational scheme. Okay, so we next show the analyzed field of Jacob FGO. And this figure shows the long-term mean climatology of the surface field from left to right, sea surface temperature, sea surface salinity, and sea surface height, and eddy kinetic energy, which measure the intensity of mesoscale eddy activity. And similar to other existing products, Jacob FGO reasonably capture large-scale feature of temperature, surface temperature, salinity, and circulation field. For example, warm pool in the tropics or highest subtropical maximum sea surface salinity, as well as subtropical gyre in this region. And the notable feature of this product is better representation of eddy kinetic energy, which is an important measure of eddy strength of mesoscale eddies. While existing products that cannot explicitly resolve ocean mesoscale eddy tend to have weaker eddy activity, this product can reasonably capture the spatial pattern of eddy kinetic energy in the global ocean. For example, a region with elevated mesoscale eddy activity in the western boundary current, such as the Kuroshio, Gulf Stream, and Agares current region. And we also validated the 3-dimensional structure of temperature and salinity field analyzed in Jacob FGO. And here we show a comparison of 3-dimensional temperature and salinity for global domain and several subdomain of the global ocean. And although there are some regional bias do exist, but our extensive comparison of the analyzed field revealed that three-dimensional temperature and salinity field, which characterize the water mass structure, is agree well with the observation. And also, another important feature is the surface velocity field. And while the non-eddy-resolving product tend to underestimate the western boundary current jet, this product can reasonably reproduce the spatial pattern of surface circulation. And here we show the long-term chromatology of surface velocity field and its intensity speed by colors. And and also we compare the volume transport of Jacob FGO across several major passages. And we found that the estimated value reasonably agree with the other direct estimates of observation, while some quantitative bias do exist, especially for the weaker cross-shear and weaker anti-Arctic current. So these results suggest that although this product is skillful at representing surface circulation, but there may be some room for further improvement, such as a model physics or data assimilation scheme. And so far, we have focused on time of mean feature, but we also look into the temporal variation in oceanic field. And as an example, here we show the animation of sea level height anomalies from satellite observation and those from FGO. And you can see this shape and intensity of individual eddies reasonably captured in our Lianer's field and seen in the observation. And to demonstrate that feature more in an objective manner, we have calculated correlation coefficients of sea surface height from observation with those from Jacob FGO here. And you can see a very region of high correlation in tropics, because in this region, sea level fluctuation is largely determined by wind forcing and its volcanic response. But high correlation region also extend to extratropical region, such as cross-shear extension region and Agaras region. One may think this is kind of a natural result because this model assimilates satellite sea surface height data to correct the model state. But if we calculate a similar statistics correlation using non-eddy-resolving product, we obtain a dramatically different picture. So similar to FGO, other non-eddy-resolving products have a higher correlation in the tropics, but correlation rapidly drop off to the extratropical region. So important thing is both of these two products assimilate same sea level data to correct the model. So this result suggests that the use of eddy-resolving ocean model is critical to better representation of observed eddy-like features and associated water mass pattern. And we further check the long-term trend of steric sea level trend to see whether this product may be used for monitoring long-term change in the climate system. And here we compare the sea level trend derived from satellite observation and those calculated from those derived from steric sea level trend of Jacob FGO. And the global mean time series is shown in this panel. So you can see that regional pattern of steric sea level trend is such as accelerated sea level rise in the subtropical regions seen in observation is also well captured in our system, although some quantitative discrepancy do exist. and the trend somewhat underestimated compared to the observation. These results, extensive validation against observation, shows that our newly developed product are skillful at representing three-dimensional temperature salinity field, as well as the circulation and their time variation. So it may be useful to monitor small ocean, frontal scale ocean variability. And before moving to the forecasting part, I provide you some application of this product to study of on the assessment of impact of the river runoff on the ocean circulation and salinity fields. And here we try to, in order to assess the impact of river runoff onto the representation on the ocean salinity field and sea surface height pattern, we have produced an additional reanalysis experiment that does not use river runoff forcing to obtain the first guess field. And here, as an example, here we show the snapshot of sea surface salinity and sea level anomaly. And from satellite observation, the top one is satellite observation, and lower panel is from the original Jacob FGO that includes river forcing. And lower panel shows those from experiment without river and forcing. And you can see that region, tank of low salinity water near the coast, which is related to outflow of fresh water from Mississippi River, is largely absent in the experiments, a simulation run without river forcing. And yeah, similar feature can also see in the time series of sea surface salinity here. So these results suggest that explicit inclusion of the river run forcing are crucial for better representation of low salinity water and its spreading to the open ocean. So yeah, as shown in this example, this product may also use to some kind of a sensitivity experiments. So in concluding this session, we briefly introduce how the access to the data. And as shown in this screenshot of our website, our product is publicly open to the public. And because the data size is so large that it requires a lot of data storage, we distribute this data depending on individual interest or requests. So if you are interested in using our product, please send an email to this address or directly contact myself. Okay, so let's move on to the section focusing on the forecast path of the cross-shear and Gulf Stream jet using our newly developed forecasting system. So actually, the animation here again shows the surface velocity fields obtained from satellite observation. And you can see it is well known that the intensity of western boundary current jet, such as cross-shear and Gulf Stream, undergoes a distinct low frequency variation at interannual to decadal timescale. And such kind of variation is caused both by external forcing or deterministic forcing by the atmosphere, such as wind stress and heat flux, and also arises from internal variability of western boundary currents arising from the nonlinearity of the system. So, and recent observational modeling studies have revealed the mechanism and characteristics of this kind of the year-to-year fluctuation in western boundary current. And this kind of change in western boundary current features are important for transport of heat and other active and passive traces. And its accurate description and its accurate prediction very important for made accurate prediction of the climate system, mid-latitude climate and other marine ecosystems. So what is the source of predictability of western boundary currents? One factor that holds the key for prediction is initial memory of the ocean. And to demonstrate this point, here we show the log correlation between the speed of a Kuroshio extension jet averaged in this downstream region of Kuroshio with the sea surface height anomalies. And at the log 0, the strengthening of Kuroshio jets corresponds to increase positive anomaly of sea level height to the south and negative anomalies to the north, as expected from the geostrophic relationship. And log correlation map suggests that the positive anomaly to the south can be traced back to those in the central to eastern part of the basins that existed a few years before the acceleration of jet. So in other words, SS sea surface height anomalies are excited in the central to eastern Pacific. In case of Kuroshio extension jet, sea surface height anomalies excited in the central to eastern Pacific propagate westward as a barotropic Rossby waves and then modulate the speed of Kuroshio extension jet, like this. So based on this idea, the prediction of Kuroshio extension jet may be possible using the following strategies. First, by initializing OGCM with observed anomalies, like this kind of, by incorporating this kind of precursor signal, and then track the propagation in OGCM, and then we may obtain the future states of the Kuroshio jet in advance at the time of a few years. Okay, so to confirm the idea that I explained in the previous slide, here we have performed possibility of operational prediction of spatial temporal variation in western boundary current region using a retrospective forecast experiment that use initial condition of Nowcasting system and then integrate the model forward to track the future evolution and assess their skill in predicting the intensity of Kuroshio extension jet. So this slide summarizes our setup of retrospective forecast experiment. And in this experiment, here we have initialized the OGCM from initial state corresponding to January 1st of the de-analysis run. So this means the de-analysis field of Jacob FGO. And integrated forward for 30 months without data acceleration. So this kind of forecasts have been made for each year from 1994 to 2019. So we have conducted prediction for in total 26 cases. And to assess the impact of atmospheric synoptic or interannual variation in atmospheric field, we have performed two sets of experiments for each case. And the first one is called a LEA4 experiment. That is integration with same atmospheric forcing as the de-analysis run. So it's kind of an observed history of wind and heat flux applied to the model. So this is kind of an extreme case that all future evolution of the atmospheric state is predictable. And another experiment called CREAM4 is similar to the first one, but the atmospheric forcing field is replaced with climatological wind forcing, atmospheric forcing. So in this case, this is assumed that a future state of time variation in atmospheric state is totally unpredictable. So source of predictability only comes from the initial ocean condition. And because western boundary currents exhibit chaotic variation, so independent of forcing, and to account for such kind of internal variability, we have performed both experiments using 5 ensemble members with slightly perturbed initial conditions and for each year. So it results in a very large computational cost, but we have done this with our supercomputer facility of Jamstack. Okay, this is kind of a technical slide, but this explained how we define the western boundary current jet. And but this shows the example for Kuroshio extension jet. And we first detect closed contour of sea level height, and then calculate a geostrophic velocity. And then obtain the latitude of maximum absolute velocity and corresponding velocity, and take a zonal mean to obtain the position of western boundary current jet and its associated intensities. So the similar procedures are applied for the Gulf Stream. So here we show an example of successful prediction of Kuroshio extension jet. And this is a prediction of the Kuroshio extension jet speed from 2015, January 1st of 2015. And here we show for the left panel, it shows the speed of Kuroshio extension jet from satellite observation. And the middle panel is for LEA4 forecast, and right panel is for CRIM4 experiments. And at the time of initialization, the Kuroshio extension jet was enormously stronger than normal years. But as shown in this time series, but as time proceeds, it gradually weakened and transition into negative phase. In other words, the speed of Kuroshio extension decelerated. And this kind of distinct phase transition of the intensity of Kuroshio extension jet is reasonably predicted by our both LEA4 and CRIM4 experiment issued in January 2015. So this suggests that initial ocean memories can provide a successful prediction of this kind of change in the intensity of Kuroshio extension jet. But this is just kind of one champion case. So we try to assess the forecast skill over the entire period. And the top panel here shows the time series of Kuroshio extension jet and Gulf Stream jet. And black curve show those from the satellite observation, and blue and green ones show those from LEA4 and CRIM4 experiment. And solid curves show the ensemble mean, and thin curves from the individual ensemble member. And the lower panel show the anomaly correlation coefficient of the forecasted jet speed as a function of the lead time. And from these figures, you can see both LEA4 and CRIM4 experiments. We also show the forecast scale of persistent forecast as a reference as a black curve. And you can see that both LEA4 and CRIM4 experiments are substantially skillful at predicting intensity of both jet compared to persistent forecast. And actually, the forecast scale still exceeds 0.6 even for 2-year forecast. And so, interestingly, the forecast scale of the jet speeds generally both LEA4 and CRIM4 experiment have same degree of scale. So these results indicate a source of predictability mostly arises from the initial ocean memory rather than synoptic or atmospheric conditions. So this kind of scenario is consistent with other previous studies that address the potential predictability of western boundary current. But to confirm this idea, we try to extract some kind of precursor signal of acceleration of both Kuroshio extension and Gulf Stream jet. And to do so, here we show the rare correlation coefficients between sea level anomalies as color and wind stress by vector, and wind stress curve by Conte, and lag regression against the speed of Kuroshio and Gulf Stream jet. And at the zero lag, as shown in the previous slides, the acceleration of both KE and Gulf Stream jet corresponds to a dipole structure of sea level anomalies with positive anomaly to the south and negative anomaly to the north, consistent with the geostrophic relation. And if we go back in time to evolution of these anomalies, we can see that positive anomaly to the south can be traced back to anomalies in the interior ocean to the east, and correspondingly downwarding favorable wind and precursor are found in the same region east of the positive anomalies. And also, we also check the source of signal of the negative anomaly are rather not so evident compared to the positive anomaly. But in case of the Gulf Stream jet, there are some persistent anomaly in the high latitude region. So this may suggest some kind of remote influence from high latitude region onto the intensity of the Gulf Stream jet speed. Okay, so we also in this so far we have focused on the predictability of the speed of Kuroshio extension jet, but we also look into the predictability of the intensity of mesoscale eddy. And although the individual eddies are kind of very chaotic, like atmospheric storms, but the corrective amplitude of eddies have undergoes distinct low frequency variation associated with a change in background flow pattern. And to demonstrate this point, here we show the long-term mean eddy kinetic energy in the Kuroshio extension and Gulf Stream region here. And you can see a band of strong mesoscale eddy along the axis of jet in both jet. But if we take compare the years with stronger jet minus years with weaker jet, distinct difference becomes clear. In other words, when Kuroshio or Gulf Stream jets are stronger than normal years, the mesoscale eddy activity is elevated to the downstream region of both corresponding jets. So this suggests some kind of deterministic dependence of mesoscale eddy kinetic activity on the speed of Kuroshio and the Gulf Stream regions. So given the successful prediction of Kuroshio and Gulf Stream jet in our system, it is natural to expect there may be some scale in predicting this kind of low frequency modulation in mesoscale activity in our system. And to confirm this hypothesis, we also calculated the anomaly correlation coefficients of EK anomalies averaged over this downstream region of western boundary current region. And again, show the forecast scale as an anomaly correlation coefficient and compare it with a persistent forecast. And you can see the Lear flow in both regions. Lear flow experiment is skillful at skillful at predicting a low frequency modulation in mesoscale eddy activity in this downstream region of western boundary current region. And for CRIMPO experiment, there are moderate decrease in scale compared to the LEAR4, but still significantly skillful compared to the persistent forecast. And so these, because this kind of mesoscale eddy modulation have impact on the atmospheric circulation, and so this kind of successful prediction have implication for year-to-year prediction of extratropical atmospheric circulation and precipitation and other related fields. Okay, so let me briefly summarize this talk. And in the first part, I have introduced our newly developed semi-global ocean DNS product called Jacob FGO. And this is developed as a global extension of regional system configured for the North Pacific and covered the semi-global ocean with a horizontal resolution of about 10 kilometers. And extensive validation of analyzed field of Jacob FGO against available observation demonstrated that spatial temporal variation in various oceanic fields, such including water mass structures or ocean currents and eddy fields, reasonably reproduced in our new system compared to other existing system that does not explicitly resolve eddy, mesoscale eddy. And using that DNS field as an initial condition, we have performed a series of forecasting experiments focusing on prediction of western boundary current jets. And by using the initial condition taken from the DNS field of Jacob FGO, we have succeeded in predicting year-to-year variation in intensity of western boundary current region with a scale measured by anomaly correlation coefficients exceeding 0.6, even for 1 to 2 years prediction. And these kind of successive predictions are made by skillful, correct initialization of eddy-resolving OGCM by data assimilation. And in addition to jet speed of both jets, we also succeeded in predicting multi-year modulation in eddy kinetic energy in the downstream region, and which is deterministically connected to speed of western boundary current jet. So the above results offer some kind of operational prediction of seasonal to decadal prediction of spatial temporal variation in jets and eddy in the extratropical western boundary current region. However, it is important to recognize that these findings are purely based on a series of forced OGCM that does not explicitly account for coupling with the atmosphere. So to establish more precise estimation of predictability of extratropical oceanic feature and its impact on the climate system, further assessments with high-resolution Earth system model necessary, and I think it will be a next step to we need to proceed. Okay, this is the end of my talk, and thank you for your kind attention.
Okay, thank you. So I'd like to invite any in-person questions, and we did have 1 or 2 come in online. Okay, go on.
So if I understand you correctly, you are invoking Rossby wave propagation, westward propagation as the source of predictability. Given the spatial scale of the Rossby waves, you do not necessarily need a high-resolution model to capture that. Do you get similar prediction skill in equivalent low-resolution simulations?
That's a very important point. And actually, previous studies, especially focusing cross-shore extension jet, suggest the large-scale nature of, for example, area average sea level height field may be predictable with, how do we say, the more simplified model, even for the linear Rossby wave model. But detailed structures of eddy, such as jets, cannot be predicted by a low-resolution model that cannot resolve fine-scale structure of jets. And we believe such kind of information is important because detailed structure of the jet maybe is determined transport or pattern of SST. So also our finding is based on such kind of simplified model, but we believe a high resolution model is necessary to properly reproduce the fine-scale structure.
Okay, and Dan?
Hi, thanks for a nice talk. I also had a question about initialization. So you made the statement, if I understood correctly, that initialization of the eddy field was important for some of the predictability. And the comparison that you had offered in these predictability experiments was against persistence. So I was wondering if you had run similar experiments with an uninitialized ocean field, just a sort of random eddy field, and if that's falls significantly outside of the windows of the initialized experiments you'd run.
Yeah, actually, we haven't done any experiment with uninitialized model, but I expect that in case of uninitialized prediction, yeah, the location of initial thermal anomaly associated with eddies are not properly represented, so forecast skill may be decreased due to the improper initialization of oceanic field. But it's kind of open question, so we need to investigate more about that point. Thank you.
Okay, and we have a question from Steve.
Great talk. I have a couple questions. First, I'm curious why you force your model with NCEP CFS instead of JRA 55.
Yeah, actually, it's kind of a technical reason, and the prediction system that we configured for the Western node specific was designed to host with CFS data. But in the future, we'd like to force the model is JRA 55. But one possible reason is to NCEP CFS provides hourly atmospheric data, so it includes more high-frequency atmospheric disturbance, but it may be better. JRA 55 do also contain 3-hourly data, so it may be better to force the model and compare the sensitivity of atmospheric forcing to analyze field and forecasted result. Thank you.
And then I'm just curious if you have any thoughts on why the Gulf Stream is so much more predictable than the Croatia extension.
Yeah, that's very interesting question, and we try to investigate the reason for higher predictability of the this figure and of the Gulf Stream. And one possible reason is some kind of persistent nature of high latitude anomalies in the Gulf Stream region. But I also agree that it's kind of puzzling result because Atlantic Ocean has narrower basins and it may have limited predictability. So the other possibility is that our system may underestimate predictability of Croatia extension due to some reason, but we need to investigate that point more in detail. Thank you.
Okay, thank you. And we have an online question from Joseph Chan. So regarding the differences in the reanalysis products, observation, reanalysis correlations, how are the differences in your data assimilation systems contributing to those correlation differences? So basically, are autocorrelation length scales used in JCOPE FGO's B matrix different from those in other products?
So it means correlations between the which variable? Okay, let me check.
So there's no, yeah.
I see. Yeah, it's a little bit difficult to point out the exact reason between the use of the background covariance matrix. So yeah, to completely address the question, we need to compare what kind of background covariance matrices are used in this kind of data set. But Actually, we have tried to construct a low-resolution version of a J-corp FGO using exactly similar data assimilation scheme, but replace the OGCM with non-eddy-resolving 0.5 degree the ocean model. And in that case, we obtain a similar structure as this kind of non-eddy-resolving structure. So we, at least our preliminary result suggests such kind of details of data assimilation technique have not so important for difference in skill metrics between among products. Thank you.
Hey, thank you. Are there any? Oh, Dan has another question.
Thanks. Just because this figure came up, I was really struck by the differences in the correlation structures. And I was wondering if you had subsampled the higher resolution to 1 degree before computing these correlations. So are you getting better correlations at low resolution, or is the better correlation coming because of the higher scale, wave number features?
Yeah, actually, this comparison has been made onto the horizontal grid of satellite observation. So it's 0.25, so quarter degree resolution. So if we smooth out the map onto more coarser resolution data, such kind of scale difference might be weak due to the elimination of small scale eddy-like features. But we haven't tried that, so it's maybe an interesting point. Thank you.
Okay, do we have any additional questions? Doesn't look like we got anything online other than a thank you, great talk. So let us thank Shoichiro, because we are just about at the end of the hour.
Thank you very much. Thank you.
Great job. Here, do you want to turn off your mic? And then let me introduce you.